Good morning. Now we continue our lectures devoted to the definition of the action of the Gaussian strong random operator on the random elements in Hilbert space. Let me recall your main objects with which we work. So we have Hilbert space, which is real and separate. We have a Gaussian strong random operator here. So A is Gaussian strong random operator. We agreed to use such abbreviation in H. This means that A is a linear continuous mapping from H to L2 omega pH, and for any u from H, A of u is Gaussian. We already discussed and know that A is not necessarily a family of bounded operators in the space H indexed by omega small from our probability space. So we get a problem when we want to define the action of A onto random elements in H. And last time we discussed that maybe some tools from stochastic analysis can help us, because in stochastic analysis we already have a familiar situation, namely we know that the operation of stochastic integration with respect to Wiener process in the space of square integrable functions is exactly an example of such Gaussian strong random operator which is not bounded. And we have a definition of Ito stochastic integral and Skorokhod stochastic integral. So in this case, we have a good definition of action of Gaussian strong random operator on the random elements. And we have an idea that maybe the same approach will work in the general situation. So let's do this. And I will suppose that in the space H, we have Gaussian white noise psi, as we discussed it in the last lecture. Psi is Gaussian white noise in H. And from now, I will suppose that the sigma field of random events is generated by this psi. So from now, we assume that F is equal to sigma psi. This allows us to consider all random elements, random variables as a functionals from psi, and use the tools of stochastic analysis such as Ito-Wiener expansion, such as Fourier-Wiener transform, such as stochastic derivative, extended stochastic integral, and so on. Moreover, to simplify our work. I will suppose that A now is jointly Gaussian. With psi. So we have such two assumptions, and let me explain more detailedly what does the second assumption mean. As you remember, we have e to winner expansion for any square integrable random variable. Now, because we suppose that all random events are generated by psi. Now let us take zeta is square integrate random element It means that the expectation of the norm zeta is less than. Then I can try to get e to winner expansion of zeta. Yeah? Namely, I can organize the following random. I can take any h from our Gilbert space. Consider such a random variable zeta h. Yeah? This is a scalar product of our random element zeta and this element h from Hilbert space. Then, due to this condition, of course, this is square integrate random variable. So it has e to winner expansion now, which is unique. And I will write this e to winner expansion as follows. This is the sum from n equals 0 to infinity. an. Now it depends on h linearly and psi. As we remember, the elements of e to winner expansion now are organized as follows. We took the multilinear Hilbert-Schmidt form, symmetric. So an under fixed h is an element of symmetric part of the tensor power of h, and we know that expectation of zeta h now is equal to the sum from n equal 0 to infinity a and h. Here is mom n square multiplied and n factorial. Yeah. Here is from this and from the linearity of an with respect to h, one can conclude that an is Hilbert-Schmidt with respect to all n plus 1 variables. So please check it as an exercise that from here and here it follows that an as an n plus 1 linear form, n plus 1 is Hilbert-Schmidt form. Of course, it is not symmetric already, but still it is Hilbert-Schmidt form. Please check this. So one can consider now AN as follows. I will write A n with tilde from phi 1 phi n, and this is an element of H. Obtained from this as follows. A n with tilde phi 1 phi n is equal to the sum from k equal 1 to infinity a n e k phi n phi 1 phi n multiply on ek, where ek is as usual orthonormal basis. One can check again, please check this as an exercise, that this definition does not depend on the choice of the basis. So we have such a Hilbert valued form. Moreover, we can define an with tilde psi as a sum from k equal 1 to infinity an ek psi ek. Yeah. Again, please check that this series converge in square mean. So we have such a definition, and finally we get the expression of zeta as a sum from n equal 0 to infinity an with tilde psi. So now we have the expansion of the random element in terms of infinitely dimensional Hermite polynomials from our white noise with values in our Hilbert space H. Now let us suppose that zeta is jointly Gaussian with psi. So what does it mean? If we recall that f is sigma psi and zeta is Gaussian, jointly Gaussian, with psi, it means that zeta is a member of the linear span of values of psi. Yes, because what must hold? Zeta is the function of psi, and linear combination of this function with values of psi must be Gaussian. Yeah? It follows from here that this function is linear. So from here one can conclude that now zeta has a following very simple expansion up to 1. Yeah, that expansion, Ito-Wiener expansion of zeta has only two members, 0 and 1. It is essential thing, and this condition is essential for this, because maybe you remember from the course of probability that one can construct, for example, from 3 Gaussian independent random variables, new one, which is non-linear function from this random variables, but still has Gaussian distribution. This is not our case. We suppose that psi is jointly Gaussian. With zeta is jointly Gaussian with psi, so we have such a conclusion. And now let's go back to our Gaussian strong random operators. We assumed that A is jointly Gaussian with psi. So maybe now we can construct something which is which will serve as Ito-Wiener expansion of our operator, and it will contain only two summands. Yeah? Again, A is Gaussian strong random operator, jointly Gaussian with psi. Then we can proceed as follows. For any u which belong to our H, one can consider A action of A on U. It must be a Gaussian random element, is a Gaussian random element in H, and moreover, due to this condition, jointly Gaussian with then then one can get the Ito-Wiener expansion of this, and as we discussed before, it will contain only two summands. One is related to deterministic part. So I will denote it by alpha 0 from U plus alpha 1 from U and psi. Here is such an expansion, and moreover, what we know? We know that alpha 0 is the element of AH. We discussed this before, and we remember that one can consider the expectation of Gaussian strong random operator, and this expectation is simply deterministic continuous linear operator in our space, this alpha 0. What is alpha 1 now? If we fix U, then alpha 1 of U, let me put here comma and dot, alpha 1 from U is an element of what? This is a Hilbert-Schmidt operator, so this is an element of H. Let me denote it by H1. Why I am writing so complicated notation? Because you remember that the elements of E to Wiener expansion are the elements of the tensor product. Yeah. Now this power 1, only one coordinate related to one white noise. But in order to keep the general notation, I use this tensor product 1. But it must be H valued, exactly as we discussed before when we discussed E to Wiener expansion for random element. So we have such an operator, and due to continuity of initial Hauschian-Strong random operator in square mean, continuity of this guy, one can easily check. Please check this as an exercise that alpha 1 is a continuous linear operator acting from H to this space H 1 H. So now we have the description of any Gaussian strong random operator related to jointly Gaussian with our white noise psi through two elements, two objects. One is linear operator deterministic in H, another one is also deterministic linear operator acting here. We have such a correspondence. It is one-to-one correspondence. A is in correspondence alpha 0, alpha 1. I think that it is time to have some example. Let us proceed with example of stochastic integration, which we discussed before. So now we have such an example. When our Hilbert space H will be simply a space of square integrate random functions, non-random functions from 0, 1, sorry. This is L2 capital on 0, 1 with usual star product. Now I will define psi formally. This is time derivative of Wiener process W. Wiener process, W is standard one-dimensional Wiener process, and formally psi H is equal to Wiener integral from 0 to 1 Hs dWs. We already discussed a lot of times that this is a real example of Gaussian white noise here. And now our Gaussian strong random operator A is acting on the function U from this space as follows. It must be again a function. So I put here time argument t small, and it's equal to integral from 0 to t us dws. Again, this is the linear integral. There are no any randomness inside, so it is well defined, and we have such a random function. We discussed that this function is random element z. Moreover, it was a good problem for the regular exam and the serial referendum process to check that this integral is has continuous modification, yeah, which is for any function u, which is only square integral. Now let us see that due to this definition, of course, A is not only Gaussian strong random operator in this space, but it is evidently jointly Gaussian with Xi. So we have to find this alpha 0 and alpha 1. With alpha 0, we have no any problems because we remember that expectation of the stochastic integral is 0, and one can easily check that alpha 0 now from u, which is I just put formula expectation of A of u is 0. Don't forget that this is 0 from A to 0, 1. Please distinguish between different zeros. This is 0 from Hilbert space. This is 0 from real numbers. Now let's discuss alpha 1. Alpha 1 u psi now is the following. This is the such random function. I put here dot and put here u s dws. So it can be written in terms of psi as follows. We just take the following. We take the u, multiply here this indicator of 0 point. Yeah. And this must be must have a scalar product with psi. So I can now define our alpha 1 as follows. Alpha 1 from u, it must be element of A201. So I put here T is equal to indicator of 0 T multiply on U. Okay. Here is our alpha 1. Check that we have exactly this representation. So now one can see that we have this alpha 0 and alpha 1. Yeah. We have for every u, we must have for every t, we have an operator, we have a Hilbert valued variable. So for fixed u, we must get an operator from psi from h to some to h again, and this is operator. Yeah? For fixed u, it gives us an operator which is acting from h to h. Yeah. So let me explain it again. maybe we have to explain action of alpha 1. Alpha 1 of u must be operator from H to H. Moreover, it must be a Hilbert-Schmidt operator, and it is acting by alpha 1 u H is equal to the H, excuse me, from T is equal to the integral from 0 to T u of s H of s ds. So finally, you see that for fixed u, alpha 1 is an integral operator with such kernel. Yeah. We just have it. The kernel of alpha 1 of u as an operator has a kernel and this kernel is us when s is less than t and 0 when s is greater than t. Yeah, this is a kernel of alpha 1. Okay, now we have the construction of alpha 0 and alpha 1 in this well-known case of stochastic integral. Let's consider another example. Another example. It is also important for our considerations. When we define A as follows, let us fix some orthonormal basis. EK is orthonormal basis in H. Let us consider random variables psi k, psi ek, and we already know that this identical, independent, identically distributed standard normal variables. And now let us define a u as follows. It is sum from k equal 1 to infinity, psi k, u, ek, ek. And also it is trivial to note that this is a Gaussian-Strong random operator, of course, but this is not bounded random operator because it is also a well-known exercise from probability theory that the sequence psi k is unbounded. Actually, it grows like logarithm of square root of 2 logarithm k. Yeah? The upper limit will be equal to 1, right? Or square root of 2 logarithm, not double, but 1 logarithm of k. Okay, so we know that this is a real example of Gaussian-Strong random operator. Evidently, it is jointly Gaussian with psi. And now we can again ask for alpha 0 and alpha 1. Expectation of A equal alpha 0 is equal to 0. And now look for alpha 1. And now maybe from the definition of psi k, you can imagine that now alpha 1 u h is equal simply sum from k equal 1 to infinity. Here is h ek, here is u ek, ek. And by the way, it is easily seen due to the condition that sum u ek square is equal to the norm of u square by the Parseval identity, that this is a Hilbert-Schmidt operator as we discussed. Yeah. In previous example, it was integral operator with square integrate kernel, and here it is a Hilbert-Schmidt operator due to the such representation where eigenvalues are square summated. So now we see again that our Gaussian-Strong random operator has good elements of its Ito-Wiener expansion. And it is time to produce main definition of action of Gaussian-Strong random operator on the random elements in our Hilbert space. So, in general, when we have a Gaussian-Strong random operator, A is Gaussian-Strong random operator, jointly Gaussian with psi, then, as we discussed, it has an Ito-Wiener expansion, and u is equal to alpha 0 plus alpha 1 u psi. And now let us consider random element zeta. So let zeta be a square integrate random element in H. We discussed that then it has Ito-Wiener expansion. Moreover, I can write that zeta is equal to the sum from n equals 0 to infinity, for example, b n psi. You already know that Bn is an element of the space of the Hilbert-Schmidt symmetric linear forms, and know that this is just notation for infinity dimensional polynomials related to Bn. Now let us consider such objects. Firstly, alpha 0 from zeta. One can easily see that it does not require any special definition because this is a deterministic linear operator, as we discussed. So this is square integrate due to this condition, random element in our Hilbert space. Even it has Ito-Wiener expansion. Moreover, its Ito-Wiener expansion can be easily written. Yeah. It is alpha 0 from Bn Yeah. Here I use the, by the way, interesting statement from the functional analysis. And please check it as an exercise. The superposition of alpha 0 and Bn again is Hilbert-Schmidt. Yeah. You remember from functional analysis the superposition of Hilbert-Schmidt operator and arbitrary continuous operator is again Hilbert-Schmidt. The same holds for multilinear forms. So please check. This is multilinear Hilbert-Schmidt valid Hilbert-Schmidt form. Yeah. So this is an interlinear expansion of this guy. And now what about alpha? To do this, let us consider for any h, which is fixed, h belongs to h, and fixed, consider the following. Alpha 1 zeta of h. Yeah? It is trivial to understand that such operator alpha 1 dot h is again an element of the space of linear continuous operators. Please check this. It is not hard to check. So again, as here, it can be expanded into interlinear series. So I will write this. Okay. It is equal to sum from n equals 0 to infinity. Alpha 1 Bn h xi. Again, as before, for fixed h, this is again an element of the space of linear and linear symmetric Hilbert-Schmidt forms and so on. Everything is good in this formula, but I insist that we have much more information due to the square integrability of zeta and the fact that it is this bilinear form is Hilbert-Schmidt with respect to h. Please check that now this alpha 1 Pn, I put here dot instead of h and put here n dots instead of psi. So here we have n, here we have additional 1, is an element of h then the n plus 1. Please check this. That now we have not only Hilbert-Schmidt form for fixed h, but if we consider h together with these coordinates, then we have n plus 1 Hilbert-Schmidt form. So we have such a good relation, and of course we cannot expect that this n plus 1 linear Hilbert-Schmidt form will be symmetric. Yes, it is not expected. So what we can do, we can apply symmetrization. And now let me recall you, we discussed this in previous semester that there exists such a good operation, symmetrization. Lambda symmetrization. Lambda of alpha 1 Bn from phi 1 phi n plus 1 is equal to, and now what we can say, it is such a sum. Let me 1 over n plus 1. Here we have alpha 1 Bn phi 1, here is phi 2 phi n plus 1, yes, plus alpha 1 Bn phi 2, here is phi 1 phi n plus 1, yeah, they are okay, plus so I will take subsequently one of these arguments and put it there, yeah, so plus, and finally, unfortunately, we have to rewrite something, to erase something. Here we have plus the last one, alpha 1 Bn phi n plus 1, and here is phi 1 Bn. Yeah. Okay. So this is a symmetrization of our form. I don't need to symmetrize it with respect to these arguments because it is already symmetric. I use it. Yeah? I just take the element from this company who is placed here. Yeah? So this is a symmetrization of our Hilbert-Schmidt n plus 1 linear form. Finally, the definition of the action of the operator A on the random element zeta is following. So, definition. Zeta belong to domain of A if the following series converges square A zeta, which is by definition equal to the sum from n equals 0 to infinity lambda not only lambda, but here we have alpha 0 zeta plus sum from n equal 0 to infinity. Here is lambda alpha 1 Bn xi, and here is n plus 1 values. Okay. Yeah. This is our definition. You see, it looks rather complicated. It uses an expansion of our zeta symmetrization operator. After symmetrization, we don't know whether this expansion converges or not, and if it converges, we have such a definition. Maybe some of you who recall the construction of extended Skorokhod integral recall that maybe it is something similar. You remember the symmetrization operator and so on. Yes, it is true. And let us consider some examples of this action in order to understand that we really enlarge now the operation of stochastic integration to the action of arbitrary Gaussian-Strong random operator in Hilbert space and random elements. So let us consider examples. Now the simplest example is related to the second Gaussian-Strong random operator which we discussed in our lecture today. So I just write its action. This is a sum from k equal 1 to infinity xik. Here is u ek and ek. Now consider zeta, and I will take zeta of the special kind. Yeah, let zeta be equal to the sum from k equal 1 to infinity of xik multiply 1 over k, such a random element. I take this zeta for such a reason that now it is again jointly Gaussian with xi, so its e-to-winner expansion will contain only 2, in this case even 1 summand. Yeah. Now, as we remember, a of u u has such a representation, this alpha 0 of u plus alpha 1 of u psi, and now alpha 0 is equal to 0 and alpha 1 u psi is exactly those one expressions. So maybe I am ready to say what is alpha 1 u of h, and it is equal to sum from k equal 1 to infinity h ek u ek k. And now what we have to do, we have to put here instead of u this random element zeta. So now let us consider as we did alpha 1 zeta h, and it will be equal due to this expansion and this relation. This scalar product gives us exactly 1 xi k over k, Yes, here. So we have such a sum from k equal 1 to infinity. Here is h ek. Here is psi k over k and a k. Now we understand that if we consider elements of e-to-linear expansion, it is only one. Yes, it is alpha 1. Yes, from B. I will say B1, saying that this is B1 psi. B1 H psi, and you see this expression. So it is easy now. It is easy now to calculate its symmetrization. Now alpha 1 B1 H phi is equal to sum from k equal 1 to infinity h ek phi ek over k multiply onto ek. Yeah. This is already symmetric expansion. Yeah, already symmetric expansion. And what we have to do is symmetric. Consider its action like alpha 1 b1 psi. And you remember that we have here sum from k equal 1 to infinity. Here must be psi k star psi k divided over k ek. Yes, because here we will have psi k and here we will have psi k. We have such a weak product, and you remember that finally this weak product is simply a Hermite polynomial of degree 2. Yeah. So if we continue, we'll get the sum from k 1 to infinity, and here is psi k square minus 1 over k. This is the result. So now one can say that finally our operator A acting on the random element zeta, A acting sum is equal to sum from k 1 to infinity psi k square minus 1 over k ek. Yeah. That's all. So we have such an answer, and from the first look, it can be something complicated, but we will see another exam related to stochastic integration, and we will see that we get right definition, because in case of stochastic integration, it will coincide with our definition of extended stochastic integral. That's all for today. Mainly we discuss the definition of action of Rauschner-Strong random operator on random elements. And we see that it is related to e-to-linear expansion operator of symmetrization. Next lecture we'll continue with this definition and its properties. Thank you for attention. Maybe somebody have questions or comments, please.
Yes, I have a question.
Okay.
So the justification for this definition is just that when we have a stochastic integral, it basically does what one would expect it to do, because just by looking into the definition, it looks, well, intuitively one would just try to apply the random element to the random operator omega-wise, but that would be something completely different. Well, that might have completely different values from the actual definition. So I was wondering how one justifies this.
But you know, Alexander, the equation is following. Sometimes we cannot apply omega wise. For example, consider the same random element as I discussed, but consider not a random operator, but a random functional. Yeah. So consider such random functional f of u, which will be equal to the sum from k equal 1 to infinity psi k u e k. This is random functional, and this is again not well defined the bounded linear functional. We discussed it. Then, if we take the same zeta as before, zeta is equal to sum from k equal 1 to infinity, psi k over k e k. Then, pointwise, omega-wise action f of zeta must be the sum from k equal 1 to infinity, psi k square over k. Yeah. And it is equal to plus infinity. Sure, yeah.
Yes.
Our definition gives us here -1, and this is convergence series. Yeah. So this is a problem which random elements we want to put inside of the random operator, and actually we will see further that the main examples, of course, came from a stochastic partial differential equation, from a stochastic differential equation with anticipation, stochastic integral equation with anticipation. So then we will understand that this is appropriate definition.
Okay, thank you very much.
You're welcome. If there are no any questions, then goodbye and see you next week. Bye.